This is the story of how I, someone who knows nothing about sports, ended up making a baseball simulator based on accurate real game data. You see, a few weeks ago, I was taking a little break from my normal game dev project when my girlfriend turned on a baseball game and I found myself watching along. Now, she is a baseball mega fan, and I'm just kind of baseball curious. So, as we watched, I began to pester her with a lot of questions about the game. Things like, what are all those numbers for? Why does he throw the ball like that? Why are there so many, overweight dudes? How do they mow the grass like that? Who's this Shohei guy, and why are so many people obsessed with him? And to this last question, my girlfriend said, well, why don't you just look up his stats? That's how I ended up on this site, Baseball Savant. I was perusing through the stats pages when I realized, whoa, they collect stats on nearly everything in the game. And that's when this question popped into my head. Could we take stats from a real baseball game and turn it into a video game? Now, interestingly, MLB already makes something called Game Day 3D, which is honestly pretty impressive, but it only really lets you watch specific plays. What I want is an app where I can view a baseball game like I'm watching a friend play an old school video game. And so I began to prototype. First, I decided that I wanted this project to be a web app for maximum ease of use. So I would be using React for all the UI stuff and Three.js for everything 3D. The very first challenge was making sure I could plot the ball landing locations. The MLB Stats API actually includes these coordinates, but I really had the hardest time figuring out how these were supposed to plot onto the field. After a bit of trial and error, I eventually made this Reddit post. And luckily, someone responded and linked to a GitHub repo with this image. According to the linked codebase, home plate is at 125, 199 in MLB coordinates. Why you wouldn't have home plate at 00? I have no idea, but if it works, I suppose. And with that done, I was able to plot the ball landing locations. As you can see here, I made this pretty awful looking UI to just step through the different at-bats of the game one at a time and see where the ball landed. Now, the MLB Stats API is largely undocumented, and something I always do in cases like this is put the response JSON from one of our requests into one of these online tools to generate types for our project. This gives the TypeScript compiler a lot of helpful info that ends up speeding up the development process. For instance, here it's trying to tell me that the property might be undefined, so I should add a conditional branch. Next, I went about verifying that I could plot out the strike zone locations and checked them against the visuals on Baseball Savant. This came together pretty quickly, and at this point I was convinced that I had enough data to start recreating the game in 3D. To do that, we're gonna need a ballpark, and being from SF, Oracle Park was the obvious choice. I collected a couple reference images, dropped them in Blender, and got to work modeling. Everything in the infield of a ballpark has very specific dimensions. The tip of home plate should be 90 feet from the edge of first base. The edge of first base should be 90 feet from the center of second base. The pitcher's mound should be 60.5 feet from the tip of home plate. On the other hand, home run distance is different in every park, and must only be above a minimum value. Obviously, I'm not going to model every US ballpark, so some hits that may have been a home run in other parks might not look like it in our simulation, and that's just a caveat we'll have to live with. With a rough draft of our ballpark completed, the next challenge was plotting the pitch in 3D space. The pitch data object in the game stats gives us the starting location of the ball from the moment it leaves the pitcher's hand, as well as the initial velocity. But usually the ball has a very different velocity by the time it reaches the strike zone. This, as you could probably guess, is due to gravity, as well as air resistance, which slows the ball down, and a lift force that results from the spin of the ball. Thankfully, we don't have to compute all of that, and instead the Stats API gives us average acceleration. If we just apply this acceleration by the elapsed time, we can get a pretty decent estimation of the ball's trajectory. Alright, now that we've got the pitch plotted out in 3D space, we need to plot out the ball's trajectory off the bat. We don't have anything like average acceleration for this one, but we do have the ball's starting location, its landing location, its launch speed, and its launch angle. Now, if we just ignore any kind of aerodynamic forces, we can assume a perfectly symmetrical parabolic shape. And if we want to plot the position of the ball at time t, we can just use quadratic interpolation, and that works because, okay, look. ChatGPT wrote this function for me, and I don't understand everything about it. So if you really care how it works, why don't you just go look it up, nerd? Sorry, I didn't mean you. I was talking to someone else. Yeah, that's what happened. So where were we? I copied a bunch of stuff from ChatGPT, and then behold, my glorious ChatGPT function in action. And we also know where the ball will land, so we can send the player there ahead of time. But what about ground balls? In baseball, a ground ball is any ball that hits the ground before it's picked up by a defensive player. Now, in my simulation, that same play looks like this. You see, the stats data tells us where the ball lands and the player who picked it up, but we don't know where they picked it up. And to solve this, we might have to get a little creative. If we assume that the ball maintains its horizontal speed after hitting the ground, we can plot out its movement along the ground over time. And if we know the movement speed of the player, we can calculate how far they could have traveled since the ball was hit. Then we can begin to iterate through our simulation to find the earliest time at which the defensive player could have reached the ball. After finding that location, we can begin our simulation and send our character to that location to intercept and pick up the ball. Now, this took a bit of time to get working, and there were a number of bugs along the way. For instance, I had to make sure that the catching player did not try to intercept the ball mid-air. I also had to account for cases where the ball was moving too fast to ever be intercepted, in which case I've just increased the player's movement speed to move at least as fast as necessary to catch the ball. Because remember, we're not actually playing baseball in a simulation, we are reverse engineering a baseball game and ensuring those things happen in a simulation. It's kind of like choreographing a dance starting from the last pose. Take for example this play, where a ground ball is picked up by the third baseman and thrown to first base to get the runner out. We must ensure that the first baseman is in position at first base by the time the ball is thrown to them, and we must also ensure that the runner runs slow enough that they don't reach first base before the ball does. Okay, so I hope that all made sense, but suffice to say, one of the most interesting challenges of this whole project was finding a way to work backwards from the results and make the plays make sense visually. Speaking of visuals, it was time to upgrade our little capsule fellas. My vision for character design here was a 3D interpretation of these characters from a game called Telltale Stadium. So I took a few reference pictures and dropped them in Blender. I wanted to keep the models really simple, so I'm using a basic subdivision surface workflow here. No need for any sculpting or anything like that. In terms of body shape, I took human proportions and just made them a little thicker, if you know what I mean. Let's be real, it wouldn't be a baseball player without the iconic baseball butt. Okay, maybe we can tone that down just a little bit. After reversing his Brazilian butt lift, I began the rigging process. As expected, there were the standard suite of weight painting issues. After setting up some basic poses, I realized that animating the hands moving with the bat was extremely tedious, so I made a custom IK control for this. Basically, I set up a custom floating bone that acts as a guide for the placement of both hands, which means I can animate the player's arms just by moving the bat around like this. And this would come in handy when animating the batter's swing. I'm still a bit of a noob when it comes to animating, but this was a really fun learning experience. Basically, I was using this slow-mo reference video of Mike Trout and trying to copy key poses as different frames of the animation. I had to set up a couple other props like the strike zone and the swing circle for reference. These animations aren't perfect by any means, but nonetheless I think they were good practice. And with a few basic animations and character models, the simulation was starting to come together. Or at least look less bad. Now, one thing that you'll notice is the strike zone changes size for every player and even every swing. This is because the strike zone goes from the top of the uniform pants to halfway between the player's shoulders and the top of their pants. So, as you might guess, this is generally going to be a larger zone for taller players. It's also worth noting that even though the strike zone is most often portrayed as a 2D square, it is technically 3-dimensional, and a ball that touches the strike zone anywhere above the home plate should technically be a strike, though balls and strikes are called by human umpires, so I'm not sure how much of this really makes any difference. Then I went about adding some more visual polish, and did some basic texturing on our baseball player model. For this texture set, I experimented with doing more hand-drawn effects, where I'm using the mouse to add brush strokes instead of trying to layer on a bunch of procedural effects. Manually painting on the model was a bit more work, but I was pretty happy with the result, as simple as it is. And of course, we're going to need a nice pitching animation. I followed a process similar to what I did for the batting animation, and man, this one was pretty tricky. I actually gained so much respect for the flexibility and body coordination required to throw a pitch at this speed. In fact, I tried reenacting this pitch in my room and I nearly threw my back out, so I can attest to the fact that it's not an easy thing to do. And the pitching animation led to another tricky reverse engineering problem. You see, the ball has to leave the hand of the pitcher when it's thrown. But how do we adjust the animation to make sure that the pitcher ends the throw with their hand in the right position? Yeah, for this one I just moved the pitcher to line up with the ball's initial position. The glaring issue with this solution is that the pitcher is frequently floating in the air or underground for submarine pitchers, but I really don't feel like building a whole dynamic animation system for this, so we're just gonna call this good enough. One random thought. Has anyone been to Dimensions.com? I just recorded this because I find it kind of hilarious the niche corners of the internet I find myself on sometimes. I mean, this is a site dedicated to dimensions, like nothing but dimensions, and it's actually really well designed. And apparently you can go pro on here? Damn, a Dimensions.com pro account. Yeah, that one's going right on the Christmas wish list. Now it was time to add some other visual flourishes to our environment. First, I experimented with some different out and safe indicators. I ended up liking this much more subtle option since it was just easier to read. Our ballpark was feeling a bit empty, so I decided to add a bunch of fans as 2D sprites. I was streaming this day and actually had some help working on this stuff. Broly wrote a nice geometry node script for me that I used to generate the crowd sprites. I can control the amount of audience members by subdividing and moving vertices around on these platforms. And we've also parameterized the randomness of each seat, so it looks a little more chaotic. Then, Junie actually animated a series of 8 different audience member sprites that I randomly assigned to each seat. Next, I took some time to add a few other basic details to the park, like the giant Coke bottle and mitt. And I was a bit tired of the plain white void of the sky, so I added a sky dome and painted some fluffy clouds onto a simple color gradient texture. I think if I had to do it again, I might have gone with the sunset color scheme, but generally I'm pretty happy with how it turned out. Of course, we can't forget about the baseball grass. I combined a couple procedural wave textures into a nice grid pattern and used that mask to lerp between a light and dark green color. Now it's starting to look a bit more like a ballpark. Okay, so that's all well and good, but what about this giant scoreboard? Well, for that I actually recreated a whole scoreboard system, complete with a bunch of player stats, batting order, and a scores by inning thing at the bottom. This was actually way harder than I thought because they don't really give you this kind of information for every single play. So instead I have to go through manually and calculate these stats based on the outcome of every previous play. This was pretty tricky, but the result is that you can jump into any play of the game at any time. So if I just send you a link with the right parameters, you should be able to hop into the game in the exact same spot. One change that made the game feel a lot more cinematic was the camera system. I went with a lot of static camera angles to make it feel more like an old school baseball game. Of course, we have to have the classic overhead view when the ball is hit off the bat. The initial camera angle when the pitcher is throwing to the batter is a random one of 3 different angles. And this, I think, helps make each play feel a bit more unique. And then, each at-bat starts with a view of the scoreboard, so you have an idea of which player is batting. The guided camera system is completely optional though. If you want, you can use WASD and the mouse to fly around. This way you can just watch the game from a completely different angle. Or you could just stare at the scoreboard the whole time. I mostly use this for debugging, but I thought I'd leave it in since it's kind of fun. Alright, so if you want to play around with the app, you can do that right now. It should even work on your phone. I put a link to the site in the description, and that should take you to this schedule page, where you might have to navigate through the weeks to pick a game to view. Also, if you're interested in contributing to the project or just want to take a look at the code, the project is now open source, and I'll link to the GitHub in the video description as well. Finally, I wanted to talk about what I'm working on. This is my first video that isn't a Super G devlog, and I hope you guys found it somewhat entertaining. Truth is, I've been grinding out work on Super G for coming on 2 years now and decided I need a bit of a mental break. So for the next couple months, I'm going to be focusing on a variety of different game dev projects and putting out more regular videos here on YouTube. So I hope you guys don't mind the changing content, but I think it should be fun. I've already got some project ideas in mind, but if you have any others, feel free to drop them in the comments or in the Discord. Alright guys, thanks for watching. Please subscribe. Talk to you soon. Bye-bye.